Welcome back, everybody. Happy Halloween. Today we will continue our lessons on monodromy, and hopefully we will get to the monodromy solving algorithm in its most basic form so that we can code it in the second half of today, which will be the next lecture on YouTube. Okay, last class there was a question about why the monodromy map from the fundamental group to the symmetric group is well defined, even as a function. Okay, so I didn't know an answer off the top of my head. Here is a not as perfectly detailed as I'd like answer, but hopefully this is satisfying to you. So the first thing I want to do to kind of simplify the argument a little bit is I don't want to consider loops. Rather, I want to consider paths. So we're looking right here. And I'm looking at a path from, say, a regular value u1 to a regular value u2. Remember, these are the nice parameters of our parameter space, the ones for which the preimage has exactly d points. And if all of these paths, so if gamma naught is a path in the set of regular values, then we get these d many smooth paths upstairs. This is the main idea behind homotopy continuation. And we use the gamma trick to ensure the smoothness. So let's say we have two paths, gamma naught and gamma 1, which are homotopic to each other. Now, last lesson, I just told you what homotopic means in the context of loops, but it's the exact same idea here, just the endpoints, the start point and the end point of the paths don't have to be the same. So again, you think about a movie which deforms gamma naught to gamma 1 in a continuous fashion. So the path parameter t is, say, this axis, and then the movie parameter, let's say r, or I think last time we called it capital T, but in the notes it's called r, is the movie time. Okay, so you get the movie time, and then you get the path time. All right, so vertical slices here correspond to paths that you see if you pause the movie. Okay. Focusing on gamma naught, we have a well-defined bijection from the fiber over u1 to the fiber over u2. By taking the start points of this continuation and taking them to the end points. There's no crossing, so there's no choices to be made. These are all disjoint curves upstairs. And there's.
And that is true because these are regular points.
Yes, we are only considering paths in the regular locus. Okay, so this frees our hands from having to consider the nasty parameters.
Yeah.
Okay, so we have a bunch of disjoint curves in some copy of c to the n, which you can think of as r to the 2n, so that you can leverage your understanding from calculus and things like this. But that means I can put tubular neighborhoods around here. So just little tubes around each of these. And those tubes do not intersect each other. In other words, these curves are not getting arbitrarily close. They are separated by some positive real number at any path parameter slice. Now, the fact that this movie we're seeing is continuous means that if I wiggle from time naught to time epsilon in my infinite frame rate movie, then there exists some epsilon for which anything in that time frame gives me the exact same bijection. In other words, these curves can't wiggle so that these two paths swap in a sufficiently small neighborhood. This is a property of continuity. Okay. We have tubular neighborhoods around elements. The bijection is given by the paths, but it also might as well be given by the tubular neighborhoods. If I wiggle epsilon in my continuous movie, these paths stay in those tubular neighborhoods. And so therefore, the new paths at time epsilon define the same bijection. And so there exists an open neighborhood of 0 in my movie parameter for which this bijection stays the same. Okay, so let's call that 0, comma a. Now let's take a look at what happens at gamma a. Okay, so we know from 0 to a, we get the same bijection. What happens at gamma a? Well, there also has to be an open set. So it has to intersect the original half open set here, and then it'll extend it further.
Yeah.
And you just caterpillar along. And this tells you that the bijections induced along the way the whole time have to be constant. So homotopic paths induce the same bijection. And hence homotopic loops induce the same bijection. Because loops are special cases of paths. And then finally, that you observe that that's exactly what it means for this monodromy map to be well defined. You can pick any representative of a homotopy class, and you will get the same bijection, i.e. permutation, as you follow those solutions around. So that is the level of detail I want to go into on that proof for the sake of completeness, since I promised I would say something about it today.
And this is pretty clear.
Okay, good. Okay, continuing on. Today the goal is to get to monodromy solving. How does all of this story about monodromy and loops and fundamental groups actually help us at all in practice applications? It helps us incredibly much, so much so that solving polynomial systems based on monodromy is really state-of-the-art way of solving things in numerical algebraic geometry. And so hopefully we'll get to that so that we can put it up. Recall that the whole story of this class is looking at parameterized polynomial systems at the end of the day. So let's call fxp our usual parameter, parameterized polynomial system. And then there's a map on the parameter space. And the parameter continuation theorem says there's some well-defined number d over which, for which there's an open set downstairs, so that any element downstairs has exactly d points in the binder. Okay. More generally, if you like this language, it's useful sometimes because it tells you what to Google if you're trying to find relevant results. We're going to call this a branched cover. Now, branch covers are more general. Branch covers are maps of irreducible varieties from x to y of the same dimensions, such that the map is essentially surjective. So the smallest variety containing the image is the whole space downstairs. Maps with that property, by the way, are called dominant. The only tricky thing that one needs to consider when making the leap from this parameterized polynomial system story that we were talking about before, and this story here, is this fact here that I'm going to assume. I am assuming that this is irreducible. As of now, you have no idea how to check this or anything like this, but that's okay, because this whole story really does work essentially fine if it's not irreducible. But it's easier to describe everything if it is irreducible right now. And then at some point, if I haven't said so, somebody remind me, hey, what does this have to do when the space X upstairs is reducible? And I'll tell you. It'll be pretty clear as soon as you understand the story in the irreducible case. So we've been calling this delta downstairs the smallest variety containing all the points in the parameter space where things go wrong. We've been calling it the exceptional set. In the context of branch covers, it's called the branch locus. And then the complement of the branch locus, we're still calling regular values or regular parameters. Or if you like, endowing your mathematical objects with moral agency, they are the good points. Now, everything in the branch locus belongs there because something went wrong upstairs. And it's kind of hard to see what I mean by that in this cartoon. So we're gonna look at a one-dimensional branch cover here. So here's a curve, we project it down. And generically, there's 1, 2, 3, 4, 5 points in the fiber, albeit some of them might be complex, which is why you can't see them. For example, over here, you'll have one real, 2 pairs of non-real complex conjugates. Okay, and where are things going wrong? Well, it's going wrong where these paths are meeting, right? So this belongs in the branch locus because it doesn't have 5 regular solutions. This point is not a regular solution. The Jacobian will drop here. There's multiplicity. To convince yourself in the homotopic continuation frame of mind, think about something up here. So you got 3 real points, and as you move, that's a homotopy, and you see paths coming together. And remember that we had a theorem that said the multiplicity corresponds to the number of the paths that are colliding. Yeah. So this really does have multiplicity. Multiplicity means Jacobian drops rank, meaning you're not a simple solution, regular solution. Okay, but what went wrong is up here, not here. And similarly here, what goes wrong is here, not here, not here, not here. Everything here is fine. So things belong downstairs because something funny happens upstairs in the fiber, but it doesn't have to happen poorly uniformly among the fiber.
Just one is enough.
Just one is enough. So the subset of points upstairs, which are responsible, I'll say, for the inclusion of the downstairs points being in the branch locus, is called the ramification locus. Ramification locus lives upstairs. Branch locus is the projection of it, lives downstairs.
So when you say locus, we consider it as a subvariety. So shouldn't that be by our closure? Or this?
No,
Oh, okay.
no, I mean ramification locus at this point as a set. Okay. No, you're right. Okay. You're right. Because we took closure when we talked about branch locus, so we have to take closure. But you can think about it on the level of sets. Branch locus is the subset of parameters where things go poorly. And the ramification locus in that setting would be the set of points upstairs responsible for belonging to the branch locus. But sure, yeah, let's work with just variety. So we'll always do this closure, which means the smallest variety contained. Okay, story clear? So ramification upstairs, branch locus downstairs, also called the exceptional set. Everything other than it is regular values. And I'm only allowed to take loops in there and paths in there in order to do homotopy continuation without any funny endgame stuff or any paths crossing. Everything works great over the regular parameters. Okay. So it's called a branch cover because it's almost a cover. By cover, I mean covering the space. So what's a covering space? So this is a notion from topology. If you're happy with open sets in any setting, just think about it in that setting. Okay. So a covering space of degree D is some continuous map from topological spaces, such that for everything in the base space, Y, we call that the base space, there exists a little neighborhood. So think little ball surrounding Y, open neighborhood, such that if I look at the fiber over that neighborhood, I get a bunch of copies of that ball. Okay, so example, I take a point here, Y. There exists some neighborhood, might be really small, no promises on its size. Okay. You have D in this case 3. Disjoint union is the square bracket points. B1, B2, B3. Where each of these VIs looks exactly like UI.
This one too.
And what do I mean by looks exactly like? I mean is homeomorphic. So this is the notion of being the same in topology. And that homeomorphism is given by restricting the map. These are called sheets. They look like little sheets. Ooh, there's a ghost Halloween joke in there.
But I consider them like pancakes.
Yes.
I like that better.
Which is squished down in the dish below.
Okay. You can't actually cut holes out of the eyes because then it's not homeomorphic, but you get the idea. You can paint them on. That's covering space. In fact, I restrict it to the image of you. Is a degree D covering space.
Well, there's like 2 topologies here. Does this depend on, or I guess which topology are we thinking, and does this depend on, I guess, which?
Let me think. So I think about it in the Euclidean topology, not in the Zariski. But one is stricter than the other in the sense that all closed sets in the Zariski topology are closed sets in the Euclidean topology. So as long as the direction's fine and I'm not swapping it,
Yeah.
I think it's true in the Zariski sense as well. It's not. I mean, in the Euclidean sense.
Because you couldn't do that, the separation that we did for the paths.
Mhm.
In Zariski 7, because that is not house road.
Okay. Yeah, this is one that I always get the direction backwards on, and I have to think in the privacy of my office to get right. I won't say it on camera. Okay, great. So like, let's take a look. Here's a point, Y, in the base space. Okay, here's a little neighborhood. And look at that. They all look like little intervals. Yay! Good. Okay. Confirmed in one cartoon example. So you believe me now. Okay. Okay. So if you take a topology class, specifically an algebraic topology class, you'll learn about how this fact that you have disjoint sheets above open neighborhoods, sufficiently small open neighborhoods, means you can travel in the space downstairs by just locally traveling in your neighborhoods, then reapplying the result, getting new sheets and traveling more. Okay. And those are called lifts or homotopy lifts. And that process is really what we're doing with homotopy continuation. Is we are moving upstairs in the sheets along some path downstairs in the regular values. Okay, so homotopy lifts in the algebraic topology setting are actually computed on a computer numerically using the algorithm of homotopy continuation. If you're a complex analyst and these maps going back up are analytic functions well defined in some domain, then this is called analytic continuation. In our case, since everything's algebraic, you do get this. Okay, so you might hear these three concepts kind of conflated in this course. The least honest thing about doing so is that homotopy continuation is an algorithm, which, as we've seen in our computation lectures, sometimes doesn't get the right answer. So homotopy continuation is a best effort for computing the analytic continuation of these paths, or the homotopy lifts of path sponsors. Okay, so the least honest part about these arrows is this. Maybe this one should be wiggly. But theoretically, it's fine. You take small enough step sizes, it'll work. Okay, time for fun. Recall that we have a monodromy homomorphism. Where you take a loop inside the regular locus. Loop in u space at little u. Whoop, that's good. And out pops some permutation of the phi. So sigma gamma, which is this lives a priori, it lives in the symmetric group on the fiber, which we're calling big omega little u, because it's just a little nicer than pi inverse of u all the time. Okay. Which of course is isomorphic to just SD, because there's d points in that fiber. Permuting any d things looks like permuting the numbers 1 through d. But the image of this homomorphism is a group. And it's called the monodromy group of pi based at u. And if you consider it as a subgroup of SD, that's only well defined up to relabeling the points, right? These solutions don't have a natural labeling from 1 to d, so you just gotta pick one, and then you get a subgroup of SD. Okay, so now I want to play a game. I want to play a game. Another Halloween joke there. All right. So let's say we have some polynomial system. I only know one of its solutions. All right. So there's x squared minus 1, say, and I only know x equals 1 is a solution because I forgot negatives. Okay. I know one of these solutions. Let's call it S1. Here's an algorithm to possibly find another. I will take some random loop downstairs. Okay, so random loop. See that? Gamma. And that's no longer gamma. And I'm going to track S1 along gamma. Okay. And what pops out? Well, sigma of gamma of S1. So this is the point in the fiber defined by the endpoint of the path starting at S1 and following this loop gain. Which very much might pop over to some new point. S2.
I have a question.
Yes.
So, any random, when you take any random path, that path is in U, right?
Yes.
Okay. This path is in U. Essentially, you're looking at a member of pi1 of
Mhm.
U, right?
Yeah, that's right. Here, this lives in pi1 U,
So its homotopy lives in U,
and homotopy continuation evaluates this map
right?
at any of the start points.
Okay.
Well, hooray, I may have found a new solution. That's pretty incredible. I didn't do a start system. I didn't do a Bezier homotopy. All I did was track around some random loop downstairs. Now, to be fair, if I did an itty bitty loop, like this, drawing this loop as a triangle, that's a legitimate thing to do, and that's
Yeah.
indeed what is done on a computer. Then I might just get back to where I started. Oh well, didn't find a new one. But I might find a new one.
Mm.
Yeah. And the heuristic that you should keep in mind, which is something that I think I've been hammering home, is that this exceptional locus downstairs is really complicated. You will not get your hands on it. You should be scared of it. Ooh, exceptional locus. Okay. I draw them nicely so that we can visualize a cartoon, but in reality, for moderate sized problems, I think of this as like just a bunch of spaghetti dropped on the floor. Okay.
That's bad.
It's really messy. It's like your headphones back when those had wires. Okay. And what that means, heuristically, none of this is a theorem, is that if you choose random loops in your pocket that has the headphones in it, you're gonna get knotted up with the headphones. You're not gonna be one of these trivial loops. So it turns out random loops often produce non-trivial permutations. So it is not unlikely at all in practice, and we'll see this. It's actually exceptionally common. It's actually, yeah, it's rare to have the other case, that you get something that moves S1.
In order for a random loop to entangle with delta, wouldn't there be some kind of intersection?
No, you're only looking at a real picture. That's a really important point to
Ah,
make.
Right, because you would
Okay,
have
so
this
delta
tubular.
is codimension 1, at least 1,
Yeah.
in your base space,
Which means like that is some cubular
which
negative
means codimension
go around. Two.
2 in the real space R2K, which looks the same thing as C2K.
Yeah.
Which means one-dimensional paths never touch it.
Yeah,
And
so
by never, I mean probability 0.
a bit of a stupid question. So, yeah.
Okay. No, it's not super question at all. So if I do random triangles, not in the real space, but like with complex parameters,
Hmm.
those paths are going to be smooth. It's essentially doing the gamma trick.
Yeah.
Okay. And so I really do get something in pi 1 UU. And I'm promising you, heuristically, that if you do this in practice, you're not getting trivial things in pi 1 UU.
Hmm.
And if you're afraid of that, just make your loops bigger. Just sample from larger parameters. Okay. So great, we found a second solution. What if there's more? So if there's 100 solutions, what should I do now? Well, I should just do it again. I'll just do S1 again. Over some random loop downstairs. Oops, I got S2 again. Let me try once more. S1 again, dang. Okay, let me try again. Oop, yay, a new one. Let's call that S3.
Hmm.
I can do this over and over and over again. Trying to populate my whole solution set.
Hmm.
And that's called monodromy solving. Write down the algorithm explicitly here. Input. Polynomial system. Yeah, I won't even say that. Okay. And you output steps. Wait, sorry, we also need 1 point. That's oh. We start with this one. That's our solution bucket. Okay. And there's a beginning of a loop. So choose gamma to be the triangle from U to V to W, where these are random with any distribution you care for. Okay, so gamma will be in pi 1 UU, because generically you don't have a triangle that intersects the discriminant. And do a homotopy continuation with the starting solution. S1 over gamma. Call that S1 hat. If S1 hat is not in our solution bucket, add it. Do it over and over again. Ta-da.
Just a question.
Yeah, there should be lots of questions.
So, can I say that, like, as long as my loop is quadratic, meaning that it doesn't really intersect delta.
That doesn't mean the same thing.
No, sorry. What I meant is perhaps then it doesn't go around delta.
So it's not contractile.
Yeah.
Okay.
Then does that mean I'll get a non-trivial solution?
No, and I think you asked this question last time in a different way. So first of all, just asked, if I have something that represents a non-trivial element of the fundamental group, do I get a non-trivial permutation?
Hmm.
That is the same as asking whether or not the monodromy homomorphism has a trivial kernel,
Which is
not true because the fundamental group is a very much infinite group,
Mhm.
Whereas the monodromy group is a subgroup of S or SD.
Mhm.
Okay, who's got a problem with this algorithm? Yes, Kate. It doesn't stop. When do you stop? Well, when you've done 100 loops and you haven't found anything new. Okay.
We could, I don't know, go over homotopy classes of pi or whatever the rank of pi
Oh,
is.
yeah. Okay, so if you were able to represent a generating set for the fundamental group, then you do it over all the elements of that generating set. And maybe that's a good idea.
Or maybe, I don't know. If you know, like, the space is nice enough, you being some surface, we know the characterization of what pi 1 looks like. And in that case, we could sort of,
Sure.
you know,
Yeah, it's a good idea. Good idea. Doesn't quite work. Out of the box, at least.
okay.
Okay. The first question is, when does it stop?
Hmm.
Until you're sick of it, is the answer. Okay.
Okay.
There are better answers in special situations that we'll talk about, which are really some of my favorite theorems.
Mhm.
But the other thing that I would be concerned about is, okay, let's say I could go over every class in the fundamental group. I still don't know I'm gonna hit every point. Right? I mean, what if the image of the monodromy homomorphism is just the trivial group? Uh-oh. We need something special about this monodromy group for this process to even have a shot of working.
Mm.
What do we need for that group? Thank you. Yes, very good. So now I get to tell you what a transitive permutation group is. It's transitive if for every I and j in the numbers 1 through d, there exists Gij in G such that Gij of I equals J. Okay. Equivalently, whenever you have a subgroup of the symmetric group, you can think about this as a group acting on a set via permutations. And now that you have a group action, you can talk about orbits. Transitive groups are groups with one orbit. Okay. So let me give you an example of a non-transitive group. Think of all the ways to permute the vertices of this graph so that the graph stays the same. No, that's transitive. Think about all the ways to continuously move these vertices so that the graph stays the same. Also transitive. Oh boy. Not transitive. Okay. So this is the set of permutations. It's 4 by 1, 2, 3, 4. 1, 2, 3, 4. And the identity. Okay. 1's allowed to swap with 2. 3 is allowed to swap with 4. And you can do them both at the same time, but you're never going to get 1 over to 3. Okay. Now I have a better graph example. There you go. That's not transitive. Automorphism is background. Okay. That's why we have irreducible. That will prove that this monodromy group is transitive. Yay. How are we doing on time? Have we got time? Oh, good. Okay. Okay. Here's a fact. Shouldn't be a surprise if you're convinced at this point that subvarieties are much smaller than the varieties they live in. If you have an irreducible variety and you have a proper subvariety and you rip out the proper subvariety, what's left is path connected. Example, your variety is C. And from your first homework, you know that if you rip out a proper subvariety, you pulled out some points. It's still connected. Okay. Corollary. branch number, particular, x better be irreducible. And I rip out the ramification locus, which are all those points responsible for their images being in the branch locus. I have a path connected set. Here's x. Rip out something that leaves it path connected. Since I'm doing a real picture, I gotta use dots. In reality, I would write like a curve as a subvariety here, but then you wouldn't really see what's going on over the complex numbers. So I'm writing dots. So you should think about this as x minus the ramifications. Now let's take a point, U, in the regular locus. So I get D points upstairs. Okay. And I have to give you some permutation in the monodromy group, which sends any one element in this fiber to any other. That's what I would have to do to show to you that we're transitive. Well, what do we know? We know the space upstairs is path connected. Okay, so your adversary picks an I and a J and says, bet you can't find a monodromy element that sends I to J. And I go, I bet I can. Since it's path connected, I'll just take any old path from I to J. And then project it down. Since I and J are in the same fiber, this path projects to a loop. And this is a smooth curve in the pre-image of that loop. That is the path that I follows to get to. So you get transitive monodromy. Who cares? Oh, yeah, that's what we need for this to even have a shot at working. It really has an algorithmic consequence. Okay. If you want to know that monodromy solving has a shot at working, you better know that x is irreducible. I'll pause for questions. I'm going to eat slightly into the computer time. And before I do that, I'm also going to answer Kate's question in the most trivial way possible. We're just going to assume the input is the correct number. So this will be while the size of S is not D yet. So in other words, Kate said, how do I know when to stop? Well, I know there's 100 points because that's part of the input. Then I stop when I get 100 solutions. That's a good stopping criteria. If you want to know how many solutions there are to some polynomial system, and you want to be really, really good at answering those questions, you study enumerative geometry. Okay. Okay. So there's a good paper that explains monodromy solving. And some of the upgrades of it that you may already be bouncing around in your head. And I'll post that to the website. It's by Anton Lakin, Tim Duff, and a couple others. And Keystone Lee. And implicitly, in order to analyze these algorithms, you have to make assumptions. Okay, so this is a randomized algorithm. In what sense? Well, you're picking random loops every time. Okay. Now you're picking random loops in this loop space, which is this very infinite dimensional space, right? Even if the fundamental group is a bit more discrete, any continuous loops based at U, that's a huge space, right? So you're not going to do any analysis on the loop spaces here, but instead you're going to make some implicit assumptions, which people have done throughout the literature. And I've started calling these strong monodromy assumptions. One will seem like the strongest. It is the weakest. Okay, because you actually know that one holds in a lot of situations. The monodromy group is the full symmetric group. That may seem a little wild. It's really not. This one's bold. This says I can sample loops in my space in such a way that my probability of getting an element, any element of G pi, is constant. Together, this says, look, I'm going to think about this monodromy algorithm, but I'm going to ignore all the numerical algebraic geometry going on, really, and I'm just going to think about pulling random permutations. Uniformly at random. Each has probability 1 over d factorial of being pulled. And then I'm going to analyze this algorithm. Say, okay, under these assumptions, can I analyze this? But of course, the third one, which is implicit in what I just said, is that homotopy continuation works. Okay. So in other words, if all this homotopy continuation stuff that you're taking this class on is really just gobbledygook and only works like half the time, then I'm really not evaluating these monodromy permutations with any reliability. Okay, so I really want homotopy continuation to work. And now the questions that we're interested in are things like, how many loops do I expect to need? To find all these solutions. Under these assumptions, this is exactly the same question as there are D Pokemon. And every day I wake up and I randomly catch one Pokemon. How many days do I need to catch them all? On average, what do I expect? Right? Why? Because, okay, so I started with one Pokemon, every permutation is random, which means I'm randomly sampling from a point on this fiber, right, uniformly. And so I'm just picking some new Pokemon every time. And then how many loops do I need to do I expect? This is called the coupon collector problem. Before Pokemon, there were baseball cards. People thought about these things. And I guess before baseball cards, there were coupons. I should look into the history of this. It's not the baseball card collector problem. But yeah, okay, so it's a natural question, right? You can imagine this question shows up in several areas of mathematics and otherwise. And depending on the time I'll run through, yeah, I will run through the answer. The thing I really want you to drive home is that as soon as I made these monodromy assumptions, the question about analyzing this algorithm had nothing to do with algebraic geometry, nothing to do with numerical analysis, nothing to do with topology, and everything to do with probability and permutations. The monodromy assumptions takes algorithms from numerical algebraic geometry, and it converts questions about those algorithms into questions about probabilistic group theory. Okay. T is the number of loops. It took me. Yeah. Oh, yes. Great. Thank you. Deepak. Hi. Oh, okay. So when I say homotopy continuation works, I don't mean homotopy continuation.jl works. Albeit if homotopy continuation.jl works, that implies homotopy continuation works. What I mean by homotopy continuation working means that I can reliably follow the paths given by analytic continuation, right? So we saw that sometimes that doesn't happen. You get these path crossings. And my claim with monodromy assumption 3 is that no path crossings, everything's perfect. You always get the right permutation. Yeah, the theory behind it. So let T be the number of iterations I need to do to get all the solutions. And let Ti be the number of loops I need to find the ith new solution. After I minus 1 have already been found. Okay, so for example, let's say I have 1, 2, 3, 4, 5. Okay. And okay, let's say I get this one for free. Okay. So P1 equals 1. I only needed one thing to get my first solution. And then maybe I do a loop and I get the first solution again. I do another loop and I get the third. So then T2, this took 2 tries after I'd already found one to get it. Okay, then I spend 1, and then I do a loop, I go 1 to 1, okay, nope, 1 to 3, nope, 1 to 1 again, nope, 1 to 4. Okay, T3 is now, I think that was 4 loops after, etc. Right? And so maybe like T4 is 10, and T5 is 1,000. Okay? Then the time it took in total is 1 plus 10, sorry, 1 plus 2 plus 4 plus 10 plus 1,000. And since the algorithm is random, I can think about capital T and lowercase ti's as random variables. So all right. So now let's ask ourselves, what is the probability that after finding I minus one solutions, my next loop finds the ith?
Yeah, n minus I minus one guys left.
Mhm.
We have total n then. Okay.
Yeah, sorry, n is d.
So you assume it to be uniform, right? That's why.
Exactly. Yeah, that requires the assumption of uniformity. Right, it's how many chances I have at a success over how many chances I have. How many possible outcomes. Okay. So doing one such loop is called a Bernoulli trial. I have some probability of success, some probability of failure. And then the question of how many times do I need to do a Bernoulli trial to find a success is a geometric distribution. Okay, and the expectation, so the expected value of Ti is 1/p. This is a fact from probability and statistics that if you've taken this class, surely you remember. Okay, but otherwise you trust me. And so, since these are independent, this is the sum of the TIs, which is d over d. That's probability of finding, sorry, that's the expected number of steps I need to get the first one. Well, one. If I don't have any baseball cards, I choose a baseball card. It's going to be 2. Okay. Let's pull a d out. Anybody recognize the sum on the right?
Yeah, that's log of,
Almost.
okay.
It's a Riemann sum approximation. Of log. It's the harmonic, the dth harmonic, which is approximately, but not exactly. Yeah, it's a numerical approximation of log understood as the integral of 1/x by doing Riemann rectangles of size 1. Okie doke. So monodromy solving under the monodromy assumptions will take expectedly about d log d steps. And that is it for the theory part. I'll take questions, we'll do a break, and then we'll do a quick coding session.